solving exponential and logarithmic equations. Now for all of these questions, once we get our final answer, we're going to have to check our answers. Make sure there's no extraneous solutions so we can see what actually is a solution to the original equation. Now looking at this first question, there's no way to get the bases to be equal to each other. In other words, there's no way to write 7 as 2 to an exponent. So we have to then either rewrite it as a log, or we can take the log of both sides. So if we take the log of both sides, we'll get log of 2 to the x power equals log of 7. We're going to drop this exponent down into the front using the power rule. So that's going to give us x times the log of 2 equals the log of 7. And then to get x by itself, we divide both sides by the log of 2. That leaves us with x being equal to the log of 7 divided by the log of 2, which you type into your calculator, and you round to whatever they're asking you to round to. So let's say they were telling us to round to the nearest hundredth. To the nearest hundredth, this would be approximately 2.81. Now the other way to solve this problem would be to rewrite it as a log. So it would be log base 2 of 7 equals x. You would again type this into your calculator. You're going to get the same answer, that x is approximately 2.81. Either way, we need to check our answer. So in our original equation, when we check that, if you want to check the exact to make sure it makes sense, 2 to the log of 7, or log base 2 of 7, power has to equal 7. When you type that into your calculator, you get 7 equals 7, which means it works. So our rounded answer could be our final answer. If you were to plug in the rounded answer as the exponent, keep in mind that they're just going to be close to each other. Always try to check the exact answer. In example 2, we can solve similarly to the last problem. I can either take the log of both sides, or I could rewrite the original equation as a log. If we take the log of both sides, the exponent is going to drop down in front by the product rule. So it's x minus 3 times the log of 3 equals the log of 5. I want to get x by itself, so I would divide both sides by the log of 3. I'm left with x minus 3 equals the log of 5 divided by the log of 3. To get x by itself, I would add 3 to the other side, so x has to equal the log of 5 divided by the log of 3 plus 3. Again, if the question asked you to round to the nearest hundredth, we would get approximately 4.46. Now, if we had solved this an alternate way, we could have rewritten it as log base 3 of 5 equals x minus 3. We would add the 3 to the other side and get log base 3 of 5 plus 3 has to equal x. Still, when rounding, you get that x is approximately 4.46. Again, of course, we have to check in the original equation. So that would be 3 to the power of, it's going to be the log of 5 over the log of 3. Then there's a plus 3 and a minus 3, so they kind of cancel each other out. You can write it, you don't have to. Equals 5, and when you type that into your calculator, you should get 5 equals 5, so it checks, and this would be our rounded answer. For the third example, we can see we're using Euler's number, e, which means we're going to be making use of natural logs. First, however, I want to get e by itself, so I'm going to divide both sides by 8. That's going to cancel on this side and leave me with e to the 2x power equals 20 over 8 is just going to reduce down to 5 over 2. And then I'm going to rewrite this in log form. Now let's say you treated it normally. It would be log base e of 5 over 2 equals 2x. But I know that log base e means the natural log. So I'm going to instead write it as the natural log of 5 over 2 equals 2x. To get x by itself, I divide by 2. So we get the exact answer is the natural log of 5 over 2, the whole thing divided by 2. But if you want to get a rounded answer, it would be the natural log of 5 over 2 in your calculator divided by 2, which to the nearest hundredth is going to give us approximately 0.46. Now, we could have also, from here, taken the log of both sides. So the log of e to the 2x power equals log of 5 over 2. The 2x would drop in front by the power rule. We would divide both sides by 2 log of e. And then in the calculator, x equals log of 5 over 2 divided by 2 log of e. And still to the nearest hundredth, we would get 0.46. Again, we need to make sure we check our answer in the original equation. So e times 8, and the e is being raised to the 2x power. Instead of x, I'm going to put natural log of 5 over 2, all divided by 2. And that has to equal 20, which when you plug in the calculator, you do get 20 equals 20. So this would be my rounded answer. To solve number 4, where it's already written as a log, I'm going to rewrite it in exponential form. So that would be 7 to the 3rd power equals 25 minus x. I'm going to simplify what's on the left-hand side, so I'm going to do 7 to the 3rd power, which gives me 343. Then I subtract the 25 to the other side, and I get 318 equals negative x, which means that if I divide by 1, negative 1, x is going to equal a negative 318. But I need to check this answer. When I check log base 7 of 25 minus a negative 318 equals 3. You can simplify, but you don't have to. If you type it in the calculator, it would solve it for you, even if you didn't simplify what's inside to 343. But either way, you do get 3 equals 3. So negative 318 is your solution. In this example, we need to first get the log by itself. So we're going to subtract 4 to the other side. We get 3 log, that's base 10. It's the common logarithm since nothing else is written. We're going to divide the whole thing by 3 to again get the log by itself. You get that the log of 2x equals 4. And then I'm going to rewrite it in exponential form. So 10 to the 4th power equals 2x. 10 to the 4th power is going to give me 10,000 equals 2x. You divide by 2 on both sides, and you're going to get that x must equal 5,000. Again, we need to make sure we check. So 4 plus 3 times the log of 2 times 5,000 has to equal 16. You type it into your calculator, 4 plus 3 times the log, base 10, so you can just use the log button, of 2 times 5,000, and you should get 16 equals 16, so it is a solution. It's not extraneous. In this example, we're going to simplify first. So we're going to use the property that the addition of 2 logs is the same thing as the log of the product. So you get that the log of x squared, the outer gives me a negative 1x, the inner gives me a positive 2x, so that leaves me with a positive 1x, and the last gives me a negative 2. Now I'm going to rewrite this in exponential form, so 10 to the first power equals that trinomial. So 10 to the first power equals the x squared plus x minus 2. I'm going to subtract the 10 to the other side to get it into standard form so that I can factor if possible. So I'm looking for two factors of negative 12 that add up to positive 1 and have different signs. That's going to be a positive 4 and a negative 3. Break it apart, I get x plus 4 equals 0, means that x equals negative 4. And x minus 3 equals 0, means that x equals a positive 3. But I need to check my answers. So when I check at negative 4, I get the log of negative 4 plus 2 plus the log of negative 4 minus 1 has to equal a positive 1. Well, this is the log of negative 2 plus the log of negative 5 equals 1. You cannot take the log of a negative number. It's undefined. So therefore, x equals negative 4 is an extraneous solution. But I'm also going to check the 3. So log of 3 plus 2 plus the log of 3 minus 1 has to equal 1. You get that 1 equals 1, so x equals 3 is the only solution. In the 7th example, we're going to use, again, the rule that logarithms that are being added together is the same thing as the log of the product. Now, since it's the natural log of this whole left-hand side and the natural log of this whole right-hand side, a log on both sides, whether it's natural or not, cancels. So we're left with, when we FOIL, x squared. You have a minus 2x and a plus 4x, so that's a plus 2x. And minus 2 times plus 4 gives me a negative 8. And that equals 7. I'm going to subtract the 7 to the other side to get it into standard form. And now I'm going to factor if possible, otherwise I'd have to complete the square or use the quadratic formula. So I'm looking for two factors of negative 15 that add up to positive 2 and have different signs. That's going to be a positive 5 and a negative 3, so x plus 5, x minus 3. We break it apart. When x plus 5 equals 0, that means that x equals negative 5. When x minus 3 equals 0, that means that x equals positive 3. And then the last step is to check our answers. When we check negative 5, we get the natural log of negative 5 plus 4 plus the natural log of negative 5 minus 2 equals the natural log of 7. So that means the natural log of negative 1 plus the natural log of negative 7 equals the natural log of 7. Now, even with natural logs, the natural log of a negative number is undefined. Therefore, negative 5 is an extraneous solution. When we check 3, we get the natural log of 3 plus 4 plus the natural log of 3 minus 2 equals the natural log of 7. So the natural log of 7 plus the natural log of 1 equals the natural log of 7. Again, you don't have to simplify. However, in the calculator, when you take the natural log of 7, you get a decimal. When you take the natural log of 7 plus the natural log of 1, if you wanted to, you could use the product rule. So this is the same thing as the natural log of 7 times 1, which is just 7. You show that they're equal, or you could show that their decimals are equal to however many decimal places, but either way, this is a solution.